Welcome to the AMS section on number theory. So next up we have Bretz and McBryde talking about optimal bounds of the pi event using Zagier.
Good morning. I'm Bretz from Hawaii, and this is my colleague McBryde from Alaska. To cut our Q&A a little bit short, I'm going to preemptively answer the most important questions you'll have at the end of this talk. No, I don't surf. And no, he doesn't live in an igloo. Anyway, I'd just like to say that as undergraduates, we're really excited to be here, and we hope you enjoy our talk on elementary number theory, even if it is in elementary. We began by studying the prime counting function about a year ago. We investigated a paper by the mathematician Zagier, who gave a summary of a proof by Chebyshev, which found the pi event. The special thing about Zagier's proof was how it used relatively simple induction, or easy to understand math and induction, in comparison to other proofs which use more complicated math but obtain better bounds. What really intrigued us, however, was how another mathematics student, using Zagier's method of induction, but with a much larger base case, got better bounds than Zagier did. We asked ourselves a natural question: if a larger base case gives you better bounds, what then are the best bounds that can be obtained using Zagier's method? To answer that, I'm going to begin by explaining what Zagier did. So Zagier, for the upper bound, he used strong induction starting with n smaller than 1200. He used the property of the above binomial coefficient, the fact that it contains all the primes between n and 2n. Then he used that to show that n to the power of the number of those primes will be less than 2 to the power of 2n. With some simple algebraic manipulation, he completed the induction with evens. For the odds, Zagier used the fact that pi of 2n plus 1 will be smaller or equal to pi of 2n plus 1. Combining that with what he already proved for the evens and some more manipulation, we get the completed induction for the odds. So that was the upper bound. What about the lower bound? For the lower bound, he used the above lemma and its resulting corollary. Coupled with the binomial expansion of 2 to the n, we get these two inequalities above, and then we apply a cutoff point he applied a cutoff point of 200 to get to the inequality you see there, pi of n, that's greater than 2/3 n log n, which is the lower bounds. So now that I've explained what he did, I'm going to give that to my colleague McBryde to explain what we did.
We began by using Zagier's proof with a generalized upper limit m and arbitrary base case for n less than capital N. And following steps from Zagier's proof, we arrived at the inequality highlighted in blue. And the question we had asked was what values of m would satisfy this inequality. We first noted that m has to be greater than log 4, because if it were equal, the inequality would not hold for any n. We then found a function that was sufficient to satisfy this inequality, and that's highlighted in blue. And any value of m greater than this for a given n would satisfy the inequality, while the optimal value of m would just be what is equal. For n equals 1200, the base case that Zagier used, we note that this is very similar to the value he chose, which was 1.7. We also note that this converges quite slowly towards log 4. The 10 to the 19th case is the case that the elementary number theory student used to improve the bounds the first time. For the odds, we again followed the same procedure that Zagier used and arrived at the similar inequality highlighted in blue. And the function we found was a little bit more complex than that of the evens, but the function at the bottom there is the optimal bound, or the optimal upper limit for n. So with these two functions we found, we recall that the proof Zagier used uses induction on pi of n for values less than capital N, and then evaluates the function for m at this point. So our question was, how does this behave as the base case gets arbitrarily large? And simply using calculus and well-known properties of limits, we find that both of these converge to log 4 as this base step gets arbitrarily large. The lower bound followed very quickly from Zagier's proof because it was not even an induction, it was simply a cutoff point for this function k, and the question was simply, well, how does this behave as this cutoff point gets arbitrarily large? And again, using simple college calculus, we find that this converges to log 2 as this cutoff point gets arbitrarily large. So in conclusion, the optimal bounds that can be obtained with Zagier's method are log 2 n over log n and log 4 n over log n for the upper bound. And in conclusion, we'd like to thank the Joint Math Meetings for having us, and our professor, Dr. Zagier, for taking his own time to teach us about elementary number theory and get us interested in it. And last but not least, we would like to thank you, the audience, for your time and attention. We hope you have enjoyed our talk on elementary number theory. Thank you.
We have time for a couple of questions. If not, let's thank the speakers again.